Good morning. Thank you for the introduction. I'm very happy to be here to start the second day of Q2B in Paris. So I'm going to present in this talk. I would like to give you a bit of physical understanding of why the platform we develop at Quandela is extremely efficient in terms of resources to reach fault tolerance. Can I have the slides, please? I have the slide, maybe? Yes, sorry, I didn't know about that. Okay, so as it was mentioned, I'm a scientific advisor and co-founder of Quandela and Senellart research director at the Center for Nanoscience and Nanotechnologies in Saclay near Paris here. So you had a beautiful talk yesterday from Shane Mansfield, so I will be very fast just for those who were not there to just summarize in one slide what Quandela is today. So it's a company founded in 2007. We've been commercializing quantum devices since 2018. Now we are a full-stack company developing hardware, and, assembling quantum processor, developing the software stack, algorithm, and of course we have Quandela Cloud that has been online for 3 years now. We develop software solution with industry, and you will see a lot of these examples today during several roundtables, and we provide machines for HPC centers, and we will deliver next week the one for Euro HPC, and I will tell you a bit about that. As I said, I am a physicist, I'm a solid-state physicist and quantum optics person, and so my objective today is really to explain why we can have a very efficient ways to fault tolerance with our platform. So let me start with some words about why quantum photonics photonic quantum technology. Sorry, it's the morning, I need to warm up. Why photonic quantum computing has gained a lot of momentum in the last few years. So there are very important reasons. The first one is that we all know by now that whatever the platform you're playing with, atom, ion, superconducting qubit, spin qubit, you name it, we know that to scale up, we will have to interconnect small quantum processors with light. So you may as well start with a quantum processor that already operates on light, and you gain a lot in momentum there. It's the only platform, photonic quantum computing, because of the use of the photon that can give you direct access to secure quantum computing, delegated quantum computing. Everything we do for photonic quantum computing is based on foundries, can be transferred to foundries, either silicon or 3-5 semiconductors, with integrated devices that are integrated together in a modular way. And last but not least, and it's not often mentioned, I think we should start looking into these numbers, what is very important to scale up is the clock rate at which your quantum computer can operate. This is this clock rate which will eventually define the size of the computation that you can actually implement. Okay. Okay, so some animations have disappeared. That's disturbing. So what I wanted to say is that also photons are very important resources as they are absolutely immune to decoherence. And this is one of the many assets we have for photonic quantum computing. So now let's discuss a little bit the different options. So I often hear that photonic quantum computers are more complicated than others to understand. And I think the reason for that, and actually it's a wrong statement, it's not more complicated than others. The reason for this impression is that there is a great diversity of possibilities to develop quantum computers with photons. So many, many different options, which is actually a very safe way to head toward fault tolerance. As you have many options, you can drop one of them if it turns out that it's not the right one. So I want first to comment, for instance, that there is 2 ways to encode the information. The first way is the one that we have adopted, is based on using the quantum particle of light, a photon, to encode the information. And then you can encode the information on any degree of freedom that you like. Frequency, polarization, time, orbital angular momentum, you name it. You have an infinite number of possibilities, and which means that you can actually encode more than 1 qubit on 1 photon. And this is a great asset. This is the encoding that has been chosen by the big companies like PsiQuantum or Quandela, but also QX and Orca. The other approach is based on encoding the information on the quadrature of the electromagnetic field. This is an approach that has been, for instance, implemented by Xanadu. These different ways of encoding the information share the same assets that I discussed just before. But what is interesting that I want to discuss with you today is they face the same challenges, The first challenge is to minimize losses. When I say that photons don't undergo decoherence, the only thing that can happen bad to a photon is that you lose it because it's scattered in the wrong direction and you lose the photon. So we need to minimize losses. And this is really one of the most important challenges. But fortunately, we have seen in the last few years amazing progress in this direction. And I want to really underline the amazing achievement that have been gathered by PsyQuantum that was reported in Nature this year, who have shown that you can really minimize losses in an integrated photonic chip to values that were absolutely unthinkable before. This shows that having raised 1 billion and working in foundries in the proper way makes things impossible happen. So they have shown that coupling light to a chip, propagating it on chip and detecting it can be done at extremely low losses. The other world record efficiency that has been reported in the last few years is the efficiency of single photon sources. And this is done, for instance, by Quandela, which has the most efficient, not only single photon sources, but entangled photon sources. And you will see that this is a great asset to scale up. Now let's go to the second challenge. The other challenge that all these photonic platforms face is the need to have a nonlinear photonic gate. Why? Because you take two photons, these are two particles with no charge, no mass, so they don't interact. So how do you make a gate with these two particles? Well, the idea is to have something intermediate, a system that is sensitive to one photon. So one photon changes the state of this intermediate system, which makes the interaction with the next photon depending on the first one. So how can we implement these nonlinear gates? And there, if you look worldwide, you have two ways of doing that. There is the first way, which is using probabilistic processes, and you see this is what has been adopted by most companies. The idea is to somehow get some nonlinearity through photon detection. So without giving you any detail, the idea is that by detecting photons, you can carve quantum states. And that works only at the cost of having a massive integration of your devices. And if you look at the numbers in the Nature papers from Xanadu and PsyQuantum about the platforms this year, you will see that these numbers are quite impressive. The other way to do these nonlinear gates is what has been developed and adopted by Quandela from the very start of the adventure, is to use an artificial atom. An atom in quantum physics is a system that can emit a photon at a time or can scatter a photon at a time. So this is a nonlinear system by definition at the single photon level. And so we use these atoms to emit single photons, and more recently, we also use them to entangle photons, which is exactly what we need to make these nonlinear gates. So this talk is about that, giving you a taste of the technology we have. We have quantum dots in microcavity, which are artificial atoms that behave as that provide a nonlinearity for gates. They are emitting photons that are very short, 100 picoseconds, which means that we can operate easily in the gigahertz range. And these devices, we have industrialized their production as very efficient single photon sources and spin-mediated photon entanglement generation. So let me give you some news about our single photon sources and our NISQ platform. So what you see here on the left is one of our devices, and on the right, one of our computers. So on the source side, we started the adventure in 2017, and we are very proud to commercialize our single photon sources worldwide in different research centers, even to some startups developing optical quantum technologies. The first version of these devices were something which were like a chip, but they were not packaged into something that is a plug and play. What has been done in the last few years, and is a very important technical milestone, is to couple a single mode fiber on top of the single photon sources, align that with 100 nanometer accuracy at 300 Kelvin, and make sure that nothing moves down to 4 Kelvin. So no displacement at all in all these 270 degrees change in temperature. And this now allows us to integrate these sources as a standalone single photon sources. So this is an apparatus that you can buy just if you want just to get single photons for some quantum studies. But that this is also the sources that we can now integrate in our computers in HPC centers. So here is a video summarizing the operation of our devices, the first generation of our computers. Sorry, oops, this is the wrong move. Yes. So here you have the source of single photon that I was mentioning before. And these photons from this source will go there into this chip, integrated photonic chip, where you have some photon propagating, interfering, and then you have detectors to read out the result of your computation. And you program this chip to make different calculations. So let me give you a virtual tour of our QPUs. So they start like this with our devices that are coupled to a fiber. Everything is integrated in this cryostat. You see it looks like a suitcase-size cryostat that you plug into the wall. You have detectors and single photon sources here. Then the device goes into what we call a time-to-spatial demultiplexer. This is the latest generation for the 12-qubit machine that we are delivering next week. And then the photons go into this photonic chip. So this is one example of a design where they will undergo quantum interferences. And in the latest version of our QPUs, we have now our own team developing the designs of this integrated photonic chip that we now package ourselves coming from different types of foundries. Finally, I want to comment here that on these chips, of course, there are some imperfections. Beam splitter will not be 50-50%, but can be 45-55%. We found ways to correct for these errors using machine learning techniques, showing that we can gain a fidelity that is very close to 100% for any unitary matrix without space restriction, despite default errors in this fabrication. So this is a machine that we will deliver next week for EuroHPC in the Center of High-Power Computing in Paris with 12 photon, 24 modes. You see the front, the back. We are very proud of the efforts of our teams who have managed to deliver this machine within 1 year as intended. And then to program these kind of machines and use them, you have all the software stack from Quandela, the Perceval, for instance, and if you cannot access yet the machine that will deliver next week in EuroHPC, you can actually connect to the cloud of Quandela, where we have the same performances. It's up 90% of the time, and we have crossed the 1,000 user threshold recently. Okay, now I want to share with you how we will go to fault tolerance and large-scale quantum computation. And for that, we will leverage the entanglement that we can generate at the source in our devices. So the motivation behind this is somehow to change a bit the paradigm of the way we do quantum computing. And instead of thinking of qubits that you have and then you untangle to perform gates, you perform gates to untangle them, the idea is actually that if you start with a state, like this is the one that I represent here, where you have many circles are photons, many lines are entanglement links. If you start with a grid-like structure here, which we call that a cluster state, you can actually perform universal quantum computation simply by measuring, making single qubit gates on one of these photons, and then measuring that state, and then deciding the next step of your computation. So this is where we're heading now. And to do that, we harness something very powerful in our system, is that our two-level system can be turned in a more interesting state if you have an electron or a hole, so a carrier of a spin trapped in the device. So then you have two spin states that can be coupled to the excited state. So these are the states that emit photons. And you have different selection rules. If the spin is up, it will emit a photon in one polarization, the polarization right. And if the spin is down, it will emit a photon in the other polarization, the polarization left. So at the beginning of the scheme, that was proposed a long time ago, actually, theory is always ahead. You start with a spin up, you have an in-plane magnetic field, you wait a bit of time, your spin will be in the up plus down superposition, and at this point you excite the system, and then when the system emits a photon, it's no longer a single photon as it was in the first version of our QPUs, but now this photon is entangled with a spin. Spin up right plus spin down left. This is spin-photon entanglement. And we can repeat that, make another gate, and then we can make the system emit another photon, and then we have now a spin entangled with two photons. So you see, we start to build these chains of entangled particles that I was mentioning before. So last year, we have progressed on these demonstrations. So I should mention that this kind of demonstration is quite unique in the world, and nobody has done that in a system that is ready for commercialization and emitting photons at high rate. And so what we have added last year is additional knobs. And you can see now that we can produce states of light and spins that are more complex. So we start to go toward this 2D architecture that I was showing you before. What we will communicate soon on, that we have now not only 4 particles entangled, but we are close to cross the threshold of 10 entangled particles. And what we can do soon, and this is something we are very excited about, is that we can turn into one of our NISQ computers, and we feed them with entangled photons, and not only with single photons. And we strongly believe that when we do that with entangled photon-based QPUs, we will reach the threshold for quantum utility. Okay, in the last part of my talk, I want to explain now why we created Quandela, and now we have really quantified the reason behind it by looking at the resources we need to reach error correction threshold. So this state here is what we call a resource state, so it's 24 photons that are entangled in a very special way, and the way these 24 photons are entangled allows us to encode a logical qubit. So basically, for us, implementing error correction with logical qubits boils down to creating this kind of photonic state. So we take that state. There are many others. We can take others, but we took that one because this is one that has been identified by being the most tolerant to losses. We can tolerate as much as 7% losses if we are able to play with this kind of state, which is excellent news. So we take that state and we try to understand how we can create that state, comparing different ways of generating photons. And so we investigate 4 cases. On the up left corner here, this is what we call the heralded single photon source. This is the technology that has been adopted by PsiQuantum to generate photons. I will explain a bit in a second how it works. And then the other 3 cases is our way of generating photons with our devices, either changes of photons or this kind of state, so we call them caterpillar. When you have more particles, they look like caterpillars here. Or we have a last option, which is basically pushing a bit further our technology, not having just one source, but multiple sources, so say 2 here, where we have spins, and then we can entangle the spin through the emission of the photon in a scheme that we call repeat until success. So how do we build this big state that we are looking for if we have different sources? So if we start with the heralded single photon sources of PsiQuantum, for instance, you have a system where you generate actually classical light, you create pairs of photons, and you have a detector that creates the nonlinearity I was mentioning before, and with this detector you can get a photon on the other side, but you're limited to very low efficiency because the state you start with is classical, so there are some limitation, intrinsic limitation that comes from there. So if you start with this kind of sources, to get one photon, you actually need to put many sources to get one photon. Each of them has a very low probability to fire a photon, but you know which one because there is a detector that tells you, hey, I have emitted a photon. So you take that, and then you need to entangle the photons to create, for instance, this kind of state here. And I show you here with this nonlinearity I was mentioning before, that, for instance, to get this state here, you need 6 photons actually, to create a 3-photon state, and the probability of success of making this entanglement is 1/32 with that circuit. Of course, there are circuits that are smarter than this one, but this is still the kind of number that you get. And then you start with this kind of building block, and you start counting how many photons you need at each step to finally get that state. Now, if we start with our sources, the one that we have commercialized from the start, we simply start with a photon for sure here, and then we go through the same process. So we will gain a lot, but not to the best that we can do. What I've shown you is that we can also create this kind of states here, this caterpillar state deterministically. So this is what we have done in the last 3 years. And now if you are able to do that, you only need to create 3 of these states and then to do some operations and to get that state. So you can see here we start to be very efficient. But the most efficient protocol has been derived here. Now that we have spins and photons, the blue are representing spins. So now, if instead of using just 1 spin, we use 12. Then we use a photon to entangle the spin. We create that state, and then that state can emit the state that we are looking for. And so comparing all these different cases, so it's like playing Lego with quantum devices and trying to optimize your stack to have the most efficient way to get the state that you want at the end. What we found is this, that the resource efficiency, which basically boils down to how many devices you need to entangle n photon. Is it 10 to the 3, 10 to the 6 more, or just the same number of photons that I have at the beginning, or I want to entangle? And then this is the maximal loss you can tolerate per component. And so what you see on this map is the heralded single photon sources. So this is what has been adopted by a company like PsiQuantum, as I mentioned. And here you have the most optimal case for us. And you see that there is simply 5 orders of magnitude difference in efficiency. And if you look at the maximal loss that we can tolerate for each photon, you see that there is also more than 2 orders of magnitude difference. So this makes a huge difference if you think of having to go to 0.1% loss, or you can tolerate few percent losses. It changes everything on the technology side. So this was a comparison with what competition can do, but of course we can do much better than that. So the message is that, sorry, I didn't comment on that. Actually, this numbers of 10 to the 5 is not the final number. The final number is that if you look at the number of devices you need to create a logical qubit, it's 10 to the 6. And this is clearly an amazing advantage. And what is also very important for us is that it clearly changed the energy consumption that you can estimate for the platform that you will develop. So this is really important. Of course, this was just a comparison with other technologies. Now we can play with our spins and photons the way we think best and actually define different protocols that optimizes as much as we can the 2 types of qubits that we are playing with, spin and photons, to gain even further for error correction. And actually, we have already 2 architectures that show the best error correction thresholds. So with this, I thank you for your attention.
Okay. Okay, we have a couple of questions from the audience. First question is, how can you ensure that the photons from different quantum dots are sufficiently indistinguishable?
Yes, so that's a very important point. So right now we've been playing with just one source. The photons emitted by one source are identical, but now we are actually working very hard and we are making extremely positive progress in making 2 sources identical. So from the literature, it's been shown that they can be identical up to 94% for now. But this was done without all the knobs that we have right now, so we have actually very promising experiment in the lab. So the way that goes in the direction of above 90% identicality, the way to do that is to quiet the solid-state environment. So it's about material science of the semiconductor and being very careful about the noise on the knobs, actually, the control knobs of our system.
Okay, great. And the second question is, does every quantum dot get its own refrigeration and laser setup?
No, of course. We can, so I cannot go back, I think, but I've shown you the cryostat where we actually, right now, we put 1 dot and like 12 detectors in a single cryostat, so we can also fiber pigtail, because the source pigtail is like 1 centimeter square in this current version of integration. So right now we can put several sources. Actually, the cooling power of this is very, very little because it's not an active component. We are actually working on miniaturizing that way more. We have ways to do that using all the tools of semiconductor packaging, and then we can put many sources in one cryostat.
Excellent. Let's thank Pascale again.
Thank you.